Implicit differentiation problems can be tough, especially when they start involving trig and the chain rule all in one. So today I wanted to show you an example of how to do this and kind of keep building on previous implicit differentiation and chain rule videos I've made by putting them into one problem. And we're going to do this using the one single easy trick that you should be able to use on basically any implicit differentiation problem. So be sure to stick around to the end so you can see how I applied this to this problem and how you can do it on any other implicit differentiation problem. Without further ado, let's go ahead and jump right on into it. So here's the problem we're going to be going over that I'm going to use to demonstrate the easy trick that you can use to keep the important information straight in your head as you're working through implicit differentiation problems. And I wanted to show you this example because it's a good example of chain rule mixed with implicit differentiation. And since my last couple of videos went over chain rule, I figured this would be a good example to go over. So when you're doing an implicit differentiation problem, that's basically just going to be one where you're trying to find the derivative of your function y with respect to x, or, depending on whatever the variable and whatever the function are, that's not really important. But what we're trying to find is the derivative of some function with respect to some variable. In this case, it's y and x. And the reason why we need to use implicit differentiation here is because we have this function that relates x and y, but we can't actually isolate y and figure out what y is in terms of x. So since we can't get an explicit function for y in terms of x, we have to use implicit differentiation in order to find the derivative of y. And usually when we're finding this derivative of y with respect to x, our answer is going to have y's and x's in it, resulting from the fact that we could not isolate y in our original equation. So when we do this, the one thing that we want to keep in mind is what is our variable and what is our function. So if we look at this, what we're trying to find is dy dx. Well, it's always going to be d something over d something, right? Whatever the letter is on top is going to be your function, and whatever the letter on bottom is always going to be your variable. So basically what that tells us is y is our function and x is our variable. Or in other words, y is a function of x. So when we're taking the derivative, we always are going to want to, since we're trying to find dy over dx, or dy dx, we want to take the derivative of this with respect to x. In other words, take d dx of this equation that we have. And when we do that, we want to keep in mind always that y is a function of x and x is the independent variable. So when we take the derivative of both sides of this equation with respect to x, wherever you see a y, there's a decent chance that you're going to have to use chain rule there. And the reason is because y is a function. So with this term here on the left, we have sine of y. Well, like I was saying in my chain rule videos recently, we have a composite function here because we're taking sine of something that is another function. So since this what's in the parentheses here, this inner function is an actual function and not just a variable, we're going to have to use chain rule. So what we can do is say that y, or what's in the parentheses here, is our inner function. And then as a result, the thing that's being plugged into, which is the sine piece, that's going to be our outer function. So chain rule tells us that the derivative of sine of y is just going to be the derivative of our outer function, leave the inside function alone. So we're going to take the derivative of sine, which is cosine, and we're going to leave our inner function as it is. So our inner function is going to remain y. And then by chain rule, we need to then multiply that by the derivative of our inner function. So the derivative of y with respect to x is just dy dx. Since we don't know what y is, we can't know what the derivative of y is. But what we can do is just say that the derivative of y with respect to x is dy dx, which literally just means derivative of y with respect to x. Now we can take the derivative of the other side of our equation. So this first term here, 3x to the fourth, this only has x in it. It only has the variable in it. So as a result, taking the derivative of that with respect to the variable, with respect to x, it's going to work the way you would expect. We don't have to do any of this weird chain rule stuff. We don't have to worry about dy dx, because the derivative of some function of x with respect to x, that's basically the methods that you've been learning about how to take the derivative of a function. So in this case, we can just find this with the power rule. So the power rule says we're going to bring the 4 down in front and multiply it by the coefficient. So 3 times 4 is 12. We're going to keep our x there, and then we're going to lower our power by 1. So 4 minus 1 is 3. Then to take the derivative of 12y, we won't really have to use chain rule, because what you want to keep in mind is if we're taking the derivative of some function of x, which y is, times some constant. So if we're taking the derivative of a constant times a function, that's just going to be that same constant times the derivative of just that constant. Well, in this case, we have a constant here and then a function of x here. So the derivative of 12y is just going to be that constant, 12, times the derivative of y. Well, the derivative of y, like we discussed over here, is dy dx. So now, once we've taken the derivative of both sides of our equation, what we want to do is add or subtract any terms that have dy dx in them to one side of our equation, and then add or subtract all of our non-dy dx terms to the other side of the equation. So you can see we have a dy dx term here, and we have one here. What we can do is just minus this over to the other side of our equation, which basically just means subtracting it from both sides. Whatever you do to one side of the equation, you need to do to the other side. And that's just going to cancel on the right side. And we're going to be left with this. So now that we have all our dy dx terms on one side of the equation, since both of these terms on the left side of our equation have a dy dx in common, what we can do is factor that out. So we can factor out dy dx from both of these terms. And if we take the dy dx out of this term, we're just going to be left with cosine of y. If we take the dy dx out of this term, we're just going to be left with minus 12. Now we only have one dy dx. So what we can do to get this dy dx all by itself now is, since we have dy dx times all this other stuff, we can divide both sides of our equation by all the stuff in the parentheses here. So doing that is just going to give us dy dx equals 12x cubed all over cosine of y minus 12. And even though this has x's and y's in it, like I said before, that's the best we're going to be able to do because we had a function or an equation at the beginning that could not be solved for y. So this is the best we can get to find dy dx. Well, I hope you found that video helpful and you realize that you can apply this trick to any implicit differentiation problem. Just be sure to keep track of which letter is your variable, which letter is your function. And if you want to keep learning about implicit differentiation or the chain rule, I have made other videos on both those topics. Just go ahead and click on one of those videos over there and see you next time. Thanks.